So good morning. Today we'll continue our discussion of ergodic Markov chains, and we'll see a number of computations that we can do at steady state on these Markov chains. One of these ergodic Markov chains that we are particularly interested in, especially for queuing systems, is birth-death type Markov chains. We've briefly touched upon this earlier, or birth-death chains or birth-death processes. And basically, this is the case when every state only has transitions to neighboring states with probability, let's say, pi plus 1, we go from here to there. With probability pi plus 1, we go from I plus 1 to I. And we may have self-transitions, but this is all basically. And then we saw, so basically the states are linearly arranged. And all transitions occur to the neighboring states. Okay, one state up or one state down. You can think of this as a birth and this as a death. And if you think about a sample path in slotted time, count the number of transitions, and think about transitions that go from I to I plus 1. At this point, we make a transition from I to I plus 1. Suppose at this other point, this is the next time we make a transition from I to I plus 1. Notice that in order to be able to make the second transition from I to I plus 1, now that we're already at I plus 1 at this point, we must have crossed from I plus 1 back to I at some point. Because otherwise, there's no way we can return. We can do this again. Okay? So this means that for every transition from I to I plus 1 at steady state, we must have a transition from I back to, from I plus 1 back to I. By this argument, the long-term frequency of transitions from I to I plus 1 are the same as the long-term frequency of transitions from I plus 1 to I, which means that pi I plus 1 must be equal to pi j pi I plus 1 I plus 1 I. Okay. This gives us, together with pi I equals 1, a set of balance equations, which you may call local balance equations, which we can easily solve to compute the steady-state probabilities. Let's apply this to a random walk with barriers. In other words, a reflected random walk. So we have states 0, 1, 2, up to m minus 1. And at every state, you either go up or down. Suppose this is the probability of moving one state up, P, and one state down, 1 minus P. Okay. Now, let's find the steady-state probabilities in this Markov chain. To compute the steady-state probabilities, let's write the global balance equations, the local balance equations, that is. Pi I times P is equal to pi I minus 1 times 1 minus P. for all I plus 1 times 1 minus p, for all I bigger than or equal to 0 and less than or equal to m minus 2. Right. So with that, we can easily show that, well, pi I plus 1 is equal to 1 minus p over p times pi I. Wait. Let's write this and find it this way. Well, pi I plus 1 equals rho times pi I, where we can define rho as p over 1, p over 1 minus p. Okay, so with that, clearly pi I is equal to rho to the I pi 0 for all I less than or equal to m minus 1. Okay, but then sum this I from 1 to m minus 1. From here, we find that pi 0, the probability of having of being at the 0 state is equal to 1 over, basically 1 over this summation. Here, let's see, yeah, it starts from 0, actually, not 1. 1 plus rho squared plus up to rho to the m minus 1. Yeah. Which you can easily sum and find that this probability is 1 minus rho over 1 minus rho to the m. How do you do that summation, by the way? 1 plus rho plus up to rho to the m minus 1. Usually, you could call it s, and then rho s will be rho plus rho to the m minus 1 up to rho to the m, and then subtract 1 minus rho times s will be 1 minus rho to the m. From here, you can easily get that s is equal to 1 minus rho to the m over 1 minus rho. So invert that, and you find pi 0. And we already have this relationship, so then pi I is equal to the rho to 1 minus rho times rho to the I divided by 1 minus rho to the m for I between 0 and m minus 1. And that is the steady state solution for the random walk with 2 reflecting barriers. Any questions? Now you may say, what is the application of this? There's a very, very important application of this, which is queuing systems. So where do queuing systems occur? Everywhere where there is a queuing phenomena. For example, there's a physical queue when we go to the bank or when we go to the cafeteria, right? You're all familiar with the lines at the cafeteria. And you may model this situation in some cases as a single server queue. If there's a single server, for example, at the bank serving all customers, that then we could model this as a single server queue. Basically, a very related model to this will be the single server geometric queue. What does this mean? Inter-arrival times and service times are both geometrically distributed. So let's see how we can model this. 0 is the state where the system is empty. For example, there's no customer at the bank. When a customer comes in, we can switch to the state 1. When another customer comes in and it's currently at the bank, we can switch to state 2, etc. And suppose the bank has room for up to m customers. Up to m customers. So now here is the model of the Geo 1Q. You don't have to really know what this means. I'm just giving it to you for extra information, essentially. Now, the model is that at any time, there can be at most one customer coming in or one customer departing, or nothing can happen. So we do not allow two customers arriving at the same time slot or two customers departing at the same time slot. So basically, let me write this down. At any time, for example, you may be measuring time in seconds to make this realistic. And it is really highly unlikely for two people to arrive at the very same second to the bank. There will be some. If seconds is not enough resolution, you can always go down in resolution, consider milliseconds, etc. Make the time resolution as fine as you need. All right, so at any time slot, okay, 0 or 1 arrivals can occur. And the probability of an arrival is, let's say, A. Okay? And at any time, 0 or 1 departures occur. Of course, when the system is not empty. When the system is not empty, of course, a departure is not going to occur. When the system has a customer in service at the moment, there is going to be a departure when the service gets completed. So when the service gets completed, the system size is going to decrease. But it is possible that there's an arrival and a departure at the same time. Right? In that case, the system size does not change. Of course, that's not true for 0. At state 0, we have a transition back to 0 if there is no arrival. That's it. Okay. So then, suppose this probability is P, this probability is Q. Okay. And the self-transition probability at these states other than 0 is the probability that either there is no arrival and no departure, or there is an arrival and a departure, right? And this will be, since we call this P and this is Q, this will be 1 minus P minus Q. Notice that P is not equal to A. Let's call probability of a departure is B, probability of an arrival is A. And what is P in terms of A and B, you think? Not exactly. Yes, please, Mustafa. A times 1 minus. Exactly. A times 1 minus B. The probability that there's an arrival and no departure. But for 0, it's different, maybe. For 0, the probability, the probability should be A, right?
We already distinguished the other condition, 1 minus P minus Q. So P actually equal to A, isn't it?
Right. Yeah, I think P should be then equal to A. Well, let's just keep the probabilities as they are for now, without associating them with A and B. This is our Markov chain, where the probability of an arrival, the probability of a state transition going up is P. The probability of a state transition going down is Q. And staying in place has probability 1 minus P minus Q. Now, how do we know that there is a steady state here? Excuse me? Yes, one recurrent class, and also it is not periodic. How do we know that it's not periodic? Self-transitions. Very nice. So by this argument that we did on the left-hand side, we can compute that pi 0, the probability of the system being empty, is 1 minus rho divided by 1 minus rho to the m plus 1, because here this state is m. This state here is m minus 1, so we replace m minus 1 by n, so we get this. If rho is not 1, what is rho here, by the way? P over Q. And if rho is 1, then the probability is 1 over m plus 1. All the states are equally likely. I'm sorry, the probability of the being in the zero state empty system is 1 over m plus 1. All right, and how about the other states? Clearly, pi I by this argument is rho to the I times pi 0 for I bigger than 0. Bigger than or equal to 0. Okay. Now, in this case, you may ask, what happens as m increases to infinity? Infinite state Markov chains are beyond the scope of our course, but just for completeness, for those of you who may be wondering, I will just touch upon this just a little bit. When n goes to infinity, okay, if P is less than Q, rho is less than 1, then pi I goes to rho to the I 1 minus rho, okay, and all states are recurrent. Okay, but if P is larger than Q, the drift is to the right, then pi I goes to 0 in this case. Here, rho is going to be larger than 1, right? And you can see that you cannot do this summation. The summation is not going to, the summation here for I 0 to infinity is not going to converge if rho is larger than 1, for equal to 1 also, for that matter. It will only converge if rho is less than 1, and then you can find finite non-zero probabilities. But for P bigger than Q, in other words, rho larger than 1, or for rho equals 1, it's not going to converge. In that case, pi i's go to 0. These two cases I write separately because in this case, all states are going to be transient. This is the situation for an unstable Q. In this case, all states are something called null recurrent. All of these terminologies are outside the scope of this course, but I'm just telling you, just in case you might be interested. Okay. So, that's all essentially for now to talk about birth-death chains. And queuing systems have a lot of applications in communication systems and networks, as well as finance and many other places. And there is a course EE 531 in our curriculum where we go into the details of various queuing systems and apply them to communication network problems in EE 532. Okay, so next thing that I want to talk about for recurrent Markov chains, positive recurrent Markov chains at steady state is two computations that we can make with them, which is mean recurrence time of a state and the first time to visit a particular state. Let's talk about the mean recurrence time. Let's define it. We have a Markov chain, and we're talking about the times between two visits to state I in the Markov chain. Okay. So we define Mi is the expected time between visits to state I. Of course, once we leave state I, we start counting the number of transitions, and we also count the first time we are in state I, and this is the total number of transitions until we come back. What is the mean recurrence time? What is the expectation, that is, of this number of transitions, and how do we find it? Basically, we will apply the same idea that we applied to finding, essentially to arguing intuitively about the steady state probability pi I. Remember, we said, okay, let's get a reward every time the chain visits state I. And then what is the long-term average rate of reward, we asked. Okay, so again, suppose Ri j of n be the total reward collected by time n, okay, given that we started in or here's our notation. In state I'm sorry, let me just say let me make this RJI. Given that we started at some state J at the beginning. Okay, so I start in some J. Doesn't really matter where I start, of course. You know that we are talking about steady state, so it doesn't matter where I start. But for completeness of notation, I'm saying this is the total reward collected from visits to state I over n time units, given that I initially start in some state J. Okay, so this is the total count of rewards. And clearly, I can get this by summing indicator random variables, and from 0 to, k from 0 to n. And now notice that as the process is renewed whenever state I is visited, the epochs between two visits to state I are independent of each other and they have the same distribution. So this is an epoch, suppose this is epoch 1, this is epoch 2. These epochs are independent and identically distributed. We abbreviate this as IID, independent and identically distributed. Then their average epoch duration satisfies the strong law of large numbers. Okay, that means the average over epochs, long-term average over epochs, or the average over a large number of epochs, is equal to the expectation of the epoch duration with probability 1. Okay. With this argument, we obtain that, and let me write it over here. The limit as n goes to infinity, Rij of n over n is equal to the 1 over mean epoch duration with probability 1. I did not do the intermediate steps. They are the subject of what we call renewal reward theory or renewal theory. And they are totally outside the scope of this course. So I'm just making you an intuitive argument. And I'm just asking you to take my word for it, essentially, that the expected time between visits converges basically the time average amount of time between epochs converges to the expected time between epochs with probability 1. And also, this is the time average reward collected. But we also showed previously, again with a similar intuitive argument, that this thing is equal to what? Pi I, the probability of observing state I. So from here we get that Mi is equal to 1 over pi I. So the expected recurrence time for a state is equal to the reciprocal of the steady state probability of that state. All right. So let's now explore this on an example. The simplest example, you remember the rain, no rain example from the very beginning of the course, of the module. So suppose the probability of going from the rainy state back to the rainy state is 0.8, and the probability of going to the no rain state is 0.2. And suppose the probability of going from no rain to rain is 0.6, and this is 0.4. Okay. Every day it rains. When it rains, it will rain the next day with probability 0.8. You know the story. Okay. So the question is, compute the expected number of dry days between 2 rainy days. How do we do this? Expected number of dry days between 2 rainy days. Any ideas? What does this have to do with the mean recurrence time of the rainy states, for example? So think about a sample path. Rain, rain, no rain, no rain, no rain, rain, no rain, 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 no rain, etc. Now, for example, this is a rainy day. Let's take this other rainy day. In between, there are 3 dry days. But it's a rainy day, here's another rainy day, and there are 0 dry days in between. So taking into account all of these cases, how do we find the expected number of dry days between any 2 rainy days? Mean recurrence time. Minus 1, right? Because when we find the mean recurrence time, that is going to also include, when we find the mean recurrence time, for example, what is the number of transitions from going from R to R here? 1. But that includes this R. Okay, so we need to take that out. So in this case, the number of transitions is 1. Take it out, 0. That is the number of non-rainy days in between. 0. Okay. So let's find the mean recurrence time of the rain states. How do we find the mean recurrence time? By this, we know that it's the reciprocal of the steady state probability. But then how do we find the steady state probability? Let me first write this down. 1 over pi rain. How do we find the steady state probability easily? Well, notice that it's a birth-death chain. So we can write the local balance equation easily, right? So pi rain times 0.2 should be equal to pi no rain times 0.6. In other words, pi rain is 3 times pi no rain. But they sum to 1. So pi rain should be equal to what? 3/4. Pi no rain is 1 over 4. Okay. So then, what is this? 4 over 3. Then what is the mean number of dry days between 2 rainy days? This minus 1. The answer to the problem is 4 over 3 minus 1, which is 1 over 3. Any questions? Okay, so now let's maybe exercise our skills on a sort of less trivial Markov chain. I'm going to write this on the board. This is the Markov chain. Suppose, self-transition probability here is 1/2. This is 1/2. I'm just going to make the numbers very easy, all 1/2s. Do we have a single recurrent class in this Markov chain? Or do we have some transient states as well? My sentence did not make sense. Do all the states form a single recurrent class, or do we have transient states among them?
4 and 5 are transient.
Very nice, Semanur. 4 and 5 are transient. So can we compute a mean recurrence time for them? Obviously not, because there's not going to be, that is, once we leave for, the amount of time until we return is not finite with probability 1, because we may never return. So therefore it's not a random variable, and we cannot compute expectation for it. So how do we find the steady-state probabilities in this chain? Do we even have to take into account 4 and 5? Can I just easily write pi 4 and pi 5 are equal to 0? I can, right? Pi 4 and pi 5 are clearly 0. Does everybody see that? They are 0 because they are transient states. So then let me write maybe 2 equations to determine these steady-state probabilities for states 1, 2, and 3 together with the normalization equation, right? So let me write an equation for this one. Pi 2 is equal to 1/2 pi 2 plus 1/2 pi 3 plus maybe 1/2 pi 4, which is 0. What am I writing here? The steady-state probability of being in state 2 should be equal to the steady-state probability of being in 2 and coming back, plus probability of being in 3 and transitioning to 2, plus the probability of being in 4 and going to 2. That, as you know, comes from the total probability theorem, the Chapman-Kolmogorov equations. Okay, I wrote this. That is equation number 1. Pi 2 basically is equal to pi 3 from this equation. Let me write another equation for this. Would you like to help me write it? Pi 3 is equal to, very nice, 1/2 pi 1 plus, maybe that's it. If you want, let's write plus 1/2 pi 5, but we already know that pi 5 is 0. Okay. So basically then that's my second equation. Pi 1 is equal to 2 pi 3 and pi 2 is equal to pi 3. So from that we know that 2 pi 3 plus pi 3 plus pi 3 should give me 1. That means pi 3 is equal to 1/4. Pi 1 is 2/4. Pi 2 is equal to 1/4. So what is the mean recurrence time for state 1? Two. What is this mean recurrence time for state 2? 4. What is the mean recurrence time for state 3? 4. Any questions? Okay. Okay, so we computed the mean recurrence time this way. In the next lecture, we will keep working on this Markov chain and then compute the probabilities, the expected amount of time until the first transition to each state and use that to compute the mean recurrence time.